Hey, teachers! Ever wonder what the charge of an electron is? Well, of course, with our modern technology, we know that they're negative. But this wasn't always the case. The year is 1897. British scientist J.J. Tomsom discovered the electron and created the plum pudding model. Notice, no electron cloud, no nucleus, complete mess. Generally, not what we know now as an atom.
As you can see, it's completely different from the orbital model we have today, but more importantly, no one knew the charges of subatomic particles. Enter Robert A. Milkian, a Columbia University alumni and professor at the University of Chicago. In 1909 to 1913, Milkian along with student Harvey Fletcher conducted the oil drop experiment.
Milkman and Harvey Specter's experiment would seek to answer the age-old question of what the charge of an electron is. Their setup was essentially an angry pressure cooker with electrified metal plates. Now, I won't bore you with the science of it all, but he will.
The oil drop experiment is set up as so. Looks pretty complicated, right? Nah, it's not. Bruh. Let's get back on track. The experiment is set up as such. An apparatus contains two metal plates. The top one is positively charged and the bottom one is negatively charged. An atomizer, located here, sprays tiny droplets of oil into the apparatus, which falls through the holes in the upper metal plate. The inside is ionized by passing an X-ray through the chamber. Upon colliding with these gas ions, the oil drops acquire a negative charge. On the sides of the apparatus are an X-ray, a microscope, and an atomizer. The microscope allowed Mustang and Factor to get a close look at individual oil droplets. The electrical charge of the plates allow the oil droplet to push against gravity, and by altering the voltage of the plates, the state of equilibrium can be found. Milman measured the mass of the oil droplet and the amount of voltage that allowed it to be in equilibrium.
By using the electric field strength formula, electric field strength equals to voltage over distance, and by substituting E to Fe, and Fe to the product of the mass of the oil droplet and gravitational force, the equation can be rearranged to mg equals to qv over d, and further rearranged to q equals to mgd over v. Now, that was all pretty complicated, so let's peel back some layers of this experiment. Our original formula is F equals to QE, in which F is our force, Q is our charge, and E is the electric field strength. E can be rewritten as V over D, V being the voltage applied to the metal plates, and D is the separation between the metal plates. Force can be re-equated to the mass of the oil drop multiplied by the force of gravity, which, once making Q the subject, becomes Q equals to mgd over V, or charge equals to mass times gravity times distance over voltage. The oil droplets go through a process called atomization, in which the bonds of the oil droplets are separated by being forced through a nozzle due to Bernoulli's principle, sort of like a wood chipper. Bernoulli's principle states that an increase in the fluid motion leads to decreased pressure of the fluid. Thus, when the fluid is forced through high speeds and low pressure, it allows for the formation of droplets. As for why Merman and Figure chose to use oil for the experiment, it was because water would evaporate far too quickly to measure any change in mass or charge.
Alright, I think that's pretty much it.
You forgot to mention the screen charge.
Ah, shucks. Right. Let me go on Google. A discrete charge distribution consists of a collection of point charges where each charge is considered as a separate entity, and the location of each charge is specified. Understood? Yeah, neither do I.
Get out of here. Discrete charges are any set of electrical charges in which each charge is considered different from another. By analyzing the properties of the oil droplets and their charges, Merman and Flanders found that the charges of electrons were distinct and not continuous.
And continuous charge refers to charge spread over any line, area, or volume, like in this diagram. Notice how the charges aren't distinct? Now, that's all we have for today's episode about Millikan's oil drop experiment. And to summarize, if you weren't paying attention,